Okay, we're back to the continuation of um, circular motion. And again, I'm not moving this to an advanced topic because, yes, while it does have a little bit of math that you need to know, I still think that it's essentially still not that advanced. Yeah, let's get into it and see what happens. Okay, so this time I don't need to have any props with me. It is vertical circular motion. As you see it here, the object is moving up and down in this circle, right? And of course, we define a radius. Um, the basic principles stay. So in any circular motion, you see the tendency. There is a force that exists radially. We know that, and that's typically what causes the tension in the string. So if this is a string, then that keeps that string tense and causes the motion. However, there is a little difference, and that's the difference I want to examine. The difference is, now as you move, if no additional force acts on the body, in the absence of additional forces, and you've only got a launch velocity v, no air resistance, but now you have gravity coming in. So the particle of mass m, as it moves here, always at any point has m times g thanks to gravity. M times g works against it, and m times g works for it, but it keeps moving. Therefore, if you said you had constant velocity, then we know if you want to launch something up, straight up with constant velocity, then the force has to be maintained all the time, and that force should be m times g or greater than that in order to get the body to accelerate. But in this case, we're going to assume no additional forces, which logically means velocity will drop as you go up here, and then velocity will pick up as you come back. So I want to do two things here. First, a little bit of math, and hopefully get it out of the way, and then we'll do some more fun things, and then we'll see how most problems get structured in this area. So what I'm going to do here is I'm going to go back here, and I'm going to say, okay, here is my radius r, right? That's my radius r, and what that would do for me is it would give me, I should probably not do that. It would probably just give me and if this was theta, so pretty much I can write the vector representation. What color shall we use today? Let's do this with, I can write a vector representation of this displacement or position, the position vector, as r times cosine theta I plus r times sine of theta j. This would be, let's say, position vector. Should probably make it in blue. So it is relatable. We know that the first derivative of displacement is velocity. And if I did the first derivative of this, and I'm not going to get into the math. If you're an A-level student, you know the math. And if you don't know the math, just take it for what it's worth. The velocity vector is the first derivative of the displacement vector, which if I do this here, what I should end up with is something that looks like r times theta dot negative sine theta I plus cosine theta j. Cosine is negative sine, theta is theta dot, so it's basically the first derivative of theta, which makes sense. We had that velocity is equal to r omega, which I think comes, you can see it applied here, right? And we know velocity effectively is along that path, right? If I was to say that that's my velocity direction. This checks out because if you see the slope of these two lines, if this is, the slope of something is it's y by x, that this would be the sine theta by cosine theta. The slope of this then is the negative reciprocal, which is basically a reciprocal would mean this way, the negative reciprocal is the other way. So it's almost like saying that this velocity vector is in this direction here. This is the velocity vector, v. You'll see that it's the negative sine theta and the positive cos theta on the y. So this cosine theta value is here, and the sine theta is on this side. So it's like taking the other direction of the displacement vector. And if you attempted to do a dot product of the two, you would see cos I and this, it's negative sine theta cos theta of I and positive sine theta cos theta for j. So if you did the dot product, there'd be 0, which means their scalar multiplication has no value. It's basically 0. That means they are perpendicular to each other. One cannot be resolved to the other. In order to resolve one to the other, we look at the cosine theta, but if they're perpendicular, anytime you try to resolve this one to that, it becomes a 0. Try to resolve that to this, it becomes 0. That's effectively what the vectors tell you, right? So that makes sense. We're there. It gives us a directional indication. But if I go one step further and say I want to really look at acceleration, now it gets interesting. Now if I get there, I have an r theta dot, double dot. This is twice the differential there. Now this is going to be negative of cosine theta and negative sine theta. I should put an I and a j, right? Now this is interesting. These are not perpendicular. This is not perpendicular. Along a cosine theta, it's negative, so it has a component on two. You can resolve this effectively on both sides, just as you resolve displacement on both axes. And you can resolve it back to the displacement as well, because if I try to multiply these two in dot product, I cannot get a 0. There is a value. As a matter of fact, it will be 1, because it will be cosine theta multiplied by cosine theta is cosine square theta with the negative out, so both positive. If I brought the negative outside, and those two multiplied with each other would be, so it would be a negative 1. A dot product was basically the scalar multiplication, so I can take a1i, and if b1j, a2i, I'm just multiplying these two and adding them up to get a magnitude value. I would see a magnitude negative 1. So if I multiply with displacement, I would have a value. Right? What happens if I multiply with velocity to see whether it's also in line with that? I would get negative sine, the positive sine and cosine. I would have here a negative sine, cosine. I would cancel it out. So I could technically say that in this case, I won't get I can't resolve it to v, but I can resolve it to r. But it doesn't cancel out with r, so it is not perpendicular to r. Is it parallel to r? It could be, but it's got a negative sign, so it's the opposite direction. So clearly there is a value here, right? We know that you get the negative along r because we saw that in the previous example. Now let's take a look and see what happens and how we understand this angular velocity's second derivative and what's causing that. And I kind of wanted to give you that idea that there is a possible, because you know that there is a, if you were doing in our previous model, we only had ay, and we were able to come up with a relationship for ay, and I think that relationship we defined as velocity times, I think that was velocity times omega or something like that, right? So you can see here, you can now see that there's a second derivative because velocity is not constant. If velocity here was constant, then this, I wouldn't even bother differentiating it because there is no, delta differential of angular speed. If angular speed is constant, would just be zero. But now this angular speed has a second derivative, so I do have a component that I need to be worried about along both sides of these axes. It's neither of them would be zero because there is a negative cosine theta here and a negative sine theta here. It has two components. So I can develop an angular velocity if I assume velocity not to be constant. That is the case here. Velocity is not constant. So I'll take this off and we'll worry about, if it was straightforward, you could make a rather simple case. But let's get to something more exciting here with this motion, right? So let's go back here and let's start with this old case that we have. I'll use another color. Let's try this. So let's start with a velocity u, right? And this time, what I want to do is I want to give my particle an angle here, right? And when it gets there, I want to give it another tangential velocity here. This time I'm going to call this velocity u, and we'll call this velocity as v because it's not the same as u, because gravity is going to be acting on it. The particle has a mass m. How do we define our particle? Let's use, wow, I'm making this really colorful. Let's use particle here, particle here. The particle has mass m. Acceleration due to gravity is known. So let's start playing with what's going on here. So as it starts off, what's going on here? In a circular motion, but in here, in green, I'm going to draw this one called mg. There is a force acting. If I was here, I would still have an mg. The mg does not change, right? The mg does not change. I do have an angle theta, alpha, anything. What I want to do now is I want to create this, okay? Now what I know is this is r, this is also r, which means this segment here is nothing but r times cosine theta, hopefully with me so far, which means I'm going to define this section here as, let's call it h for now, knowing fully well that h is equal to r minus r cosine theta, or is equal to r times 1 minus cosine theta. Okay, so far so good. I want to now introduce the concept of the conservation of energy and take a look at what's going on here. Point of interest, let's create a couple points of interest. Point of interest 1 is A. Point of interest B2 is B. So what we will do here is at point of interest A, what we have is kinetic energy is equal to half times, or rather 1/2 mass times u square, and potential energy. Now this is important when you get problems. Make sure you tell the examiner or the grader somewhere in the problem, you draw something like, like that and say PE equal to 0, or you write a line saying that, hey, this is where PE is 0, so they know, right? And then you do this at A, right? Or you just call it at A, and PE equal to 0. At B, now what happens? Kinetic energy is equal to 1/2 mass times velocity at B is V, but potential energy here, this is key, is equal to mass times G times the lift it has had, which is H, right? Now I can bring these equations together and write them in terms of familiar data, and I can actually write this as 1/2 mass times initial velocity squared is equal to 1/2 mass times final velocity squared plus m times g times r times 1 minus cosine theta. Because energy is conserved. You could do the same at this point, for example, and you could arrive at just a linear velocity in one angle. So this is going back to that projectile problem we discussed several videos ago. It's very similar. Using energy, you can actually now say, hey, if velocity only has one component here, velocity only has one component here, but somewhere in between, velocity has two components. You can now do some math to say, hey, what's going on? On kinetic energy, you wouldn't have two components, but you could resolve the using vectors. You could get two components. You could come back here and then equate it to kinetic energy, because you notice here you only have one component of velocity. But anyway, for this problem, here we are. If I rearrange this a little bit, I think I can take the mass out of all of them. I can probably eliminate the 1/2 and get the 2 here. I can actually write this problem as, or this equation as, velocity squared at any time during the motion. Velocity squared is equal to initial velocity squared minus 2 times g r 1 minus cosine of theta. Now that's an important relationship, because if you get a problem saying, hey, I've projected this out here and it's going, let's say, to some, determine at what point, and at what point would it stop going in a circle and fall? It's just easy. As soon as velocity is 0, as soon as final velocity becomes 0, that's it. Now, if you remember this is similar to v square minus u square is equal to 2as. If you remember that, right? So this is basically something similar, right? The initial kinetic energy, because total energy at 2 points conserved, you've added these two, substitute the h for the r, 1 minus cosine theta, you get the v square. I brought, left this here, u is on the other side, moved it, -1/2, and hopefully you get the formula. Right, and then you can take the square root, and then you'll have an answer. So that's typically how you want to approach these problems. The problem can ask you at what stage at what angle would the velocity become 0, for example, right? Where would the object lose its velocity? But here's a more interesting side to this whole thing, right? I'll take the vectors part out. I think this is something you can play with on vector notations to as you get problems. You'll have to figure out where you use the vector. But here's something more interesting. Now remember, this was my string of length r that's allowing me to swing this up. And obviously when it's spinning, if it was just going a straight line, there's obviously tension. We know that. How's that tension equation changing now, right? Because we saw that when we were in a clean two-dimensional horizontal plane, there was no effect of gravity. Tension was just basically equal to the force that was the acceleration times mass of the object, which was as a result of its motion itself, which we then wrote as mv squared times r. What's going on here? Well, here's an interesting situation, because it's not just that tension here. Let's go back to the tension problem. So with the energy problem, the tension problem with that, is now going to be written as T. Now what's acting on this? This is an object moving has a radial tension, but that's not it. It's not enough, because if T would have been equal to m times v squared by r, would be very similar to horizontal rotation. Here, minus something else. mg. Is it mg? Not quite. It is the component of mg, because the acceleration component is like that. That's the v squared by r acceleration. T is felt here. We want the radial value of tension. We now have to say this is the acceleration that supports me, and then what's the component that takes me off, and that's this angle here, which, if you know your geometry, is theta. That means you would get mg resolved theta, because of the geometry, cosine of theta. Net acceleration, if I took mass away, could be net force, right? Basically, I'm netting it out. If I took that out and it didn't have this, I would just be having a net value of A, which is v squared by r minus g cosine theta. That would effectively be the acceleration along this, right? Times mass gives you this tension. This is radial, r. This is radial, this is not tangential, right? So another important area to remember. So a nice way of setting up the problem could be, give you the initial velocity and then say, hey, at what point does the string lose tension? Well, there's no more tension on that string if that body's velocity, so for example, if the moment where t is 0 is effectively if it was horizontal motion, it only happens when velocity is 0, right? But if it's this way, even if there is some velocity, you have mg cosine theta killing it. So the point at which tension is lost is the point where mv squared by r is equal to mg cosine theta. M cancels out. Velocity square is equal to r cosine theta. Will give you that velocity where tension is lost. And if that velocity is arrived here, you've almost completed the circle, which means you might have additional velocity helping you to continue this. Otherwise, it reaches here, regardless of the velocity, there's no tension, which means acceleration due to gravity starts pulling it down straight this way. It's not going to follow a circle, and it's just going to go through its regular parabolic drop this way. So this is an important area, and I kind of want you to keep this in mind. We want to understand this problem from an energy perspective. We want to understand this problem from a tension, radial. So I'm looking at it radial, from the radial math. I'm looking at it from the energy side. right? And then I gave you an idea as to how you want to look at it from the vector perspective. If you want to play with the vector, you could do that. You could resolve them and obtain, vector-based value. You can come back here and say, okay, what is the component of velocity here? And then you know what the mgh here is, because it's just mgr. You know that you can then arrive at a velocity equation when it comes here. You know the change in, a function for s, which is basically the vector for s, which is r cosine theta or sine theta, and then you can use that to identify how s changes and get a value in between using s is equal to ut. You can reverse engineer the acceleration at any point, because you know s is equal to ut plus half at square. You can do the acceleration along any of these two axes and then get the square. So it's a lot more mathematics here. Usually most problems don't take you to that level of mathematics. They like to give you problems which basically take the energy and the tension equation and then try to tell you that, hey, at what point here will this begin to fall, or what velocity should I project it so it completes the circle, which means when it gets to this point, it needs to have its velocity cannot be zero. If its velocity is zero, no tension, it drops. So it needs to have a velocity greater than zero, which then means you can equate this and try and find out a value for that velocity that makes tension go low, and then anything above that is fine. So you can come back here and say this value should be greater than rg cosine theta for the circle to be complete. So hope you get that. Just want to make sure. So if you want to complete the circle, at point of interest, let's say, I'm going to take all this out and say your point of interest here is C, and I want to say that at C, right, at C, if velocity square is equal to rg cosine theta, then t equal to 0. There is no tension here, right? So the only thing acting would be mg. Like, I have an initial velocity, and then it's almost like that projectile motion where I'm just going to come down in a parabolic way, right? So to complete the circle, v square should be greater than rg cosine theta, and bring that here, right? So if v square is greater, then you can see that should be greater, right? And that's how you substitute that equation, and you'll see that, I've been given an initial velocity. I can easily tell whether I'll complete the circle or not. So a little bit of math here, but if you get the concept, you're good to go. And that's why I didn't really think it's an advanced topic. It's just about understanding how to kind of fit the motion, get the energy function, and kind of visually understanding that because I now have an mg here, I will always have a type of acceleration or deceleration. If you're going up, deceleration. If you're coming down, acceleration. It will always act in the direction of motion and not just radially. So the radial force will remain, but there will also be a component that is along the vertical, and then once you resolve them, you can always get you can always see what it means along the tangent. So you can play with that in vector sense as well. So hopefully this gives you a good idea. They've also got areas in the curriculum where they kind of combine one circle and another circle and give you an object moving along this path. But I think the math is effectively the same. Once you have to break them into chunks, you get, bits of this. So if it's this, you do the energy equations here or the vector equations, and then you do the next set on this side. But I don't see them as a complex area. It's just a question of thinking through them and reading the problem carefully. But otherwise, here you go. This is pretty much what you need for circular motion, and I won't be doing an advanced video for circular motion. I think this covers everything that up to the A levels that you would need. I will then directly go into the next part, which is I believe it's center of mass and laminas and things like that. So I'm just going to go straight into that area, which also I will just go straight through a core concept and not probably. Actually, no. For center mass, I might do an advanced video because they have a dedicated chapter just for A-level students. So I might do that in multiple videos. But here, this is good. For now, you're set with circular motion, and I'll see you in the next video.